Today's problem, we're going to look at the area under a curve. We're trying to calculate this particular area shown in the graph. Here is the graph of y is equal to 60 over x. We need to calculate the area from x equal to 1 up to x equal to 5. If we use techniques from earlier math, we can use geometrical shapes. If I draw a rectangle here, like this, and then a second one here, like this. If you notice this rectangle here, the area that's outside of the curve there, it's about the same size as the area on the inside of the curve here. And the area on the outside of the curve here is roughly the same as this area here. So we can make a calculation for this area. If this is area 1, and this one is area 2, we can make our calculation that the area is going to be approximately equal to area 1 plus area 2. And we can find these values. We have the graph of the function, we see it goes through x equal to 2 here. So our first area there is going to have a height of f of 2, multiplied by the change in x. X has changed from 1 to 3, so it's changed by 2. We need to sum the area created here, adding into this one. Here we have f of 4 as the height of the rectangle, multiplied again by the change in x, which has been 2. This particular one is going to give us, read off our values, 60 plus 30. So 90 square units. And this will calculate the area roughly under the curve in this particular period. Now, if we want to make this more accurate, we're going to need to make more calculations. To make it more accurate, we can reduce the size of the change in x. Here we had a change in x equal to 2. If we use a change in x equal to 1, we're going to be coming up to this point here, and then taking the area of this tall rectangle there. We'll repeat that again in this period, and it's going to go through here, and then we repeat again in this period. It's going to go through this point there, and then in this period it's going to go through 4.5 there. So now our areas are given by these lines, this line, and that line. This is area 2 now, area 3, area 4. Okay, so now the area can be calculated as the area is area 1 plus area 2 plus area 3 plus area 4. This is going to give us f of halfway between 1.5 multiplied by the change in x, which in this case has been 1, so multiplied by 1, plus this one. The height here is is a f of 2.5. The change in x is 1. In this one, the height of the rectangle is f of 3.5. The change in x is still equal to 1. And then this last one, the height of the rectangle is 4.5, f of 4.5, and the width is the change in x. F of 4.5 times the change in x. So this one here is going to give us 40 plus 24 plus approximately 17.14 plus approximately 13.14 And this adds up to 94.48. It's a little bit more accurate. Now, in this first example we had a change in x equal to 2. Our first height was at x equal to 2. So our first x is x equal to 2. Our second x, the change in them goes up by 2 every time, so 2 plus 2, 4. This tells us that the area is approximately f of x1 multiplied by the change in x plus f of x2 multiplied by the change in x. We can use a summation symbol for this one to abbreviate it with a sigma, and with n equal to 1 up to n equal to 2 we simply calculate f of the nth x multiplied by the change in x. And in this case we have n going from 1 to 2, x1, x2 multiplied by the change in x, which is 2. In this second time our change in x is reduced, so our change in x is equal to 1, x1 is equal to 1.5, x2 is 2.5, x3 3.5, x4 4.5. And if we wish to write it here as a summation, the area is approximately equal to, n starts at 1 and it goes up to 4. We take f of the nth x multiplied by the change in x. This will give us the area. How do we make it more accurate still? Well, obvious answer, we make the rectangle smaller and smaller. This means we reduce the change in x and let it approach 0. As the change in x approaches 0, then the number of rectangles that we're producing will approach infinity. And we can write it as the area is equal to, and then we're going to use limits. So lim as k approaches infinity, where k represents the number of rectangles we're creating. This starts at n equal to 1 and then up to k. This means that we're going to have an infinite number of rectangles we're going to surmise. So we have x to the kth x multiplied by the change in x. This will produce an accurate. We have a way of writing this notation where we show the integral of f of x with respect to x from a to b. In this case, the area here is the integral from 1 to 5 of f of x with respect to x.